Hi guys, welcome back to the next part 2 of section 3. We're going to talk briefly about average atomic mass. Average atomic mass is the number on the periodic table with all the decimal points. Basically what the average atomic mass is it is a weighted average that takes into account all the different isotopes of a particular atom. Obviously, like for example, carbon. Carbon has carbon 12, carbon 13, carbon 14. And so you would expect, well, if those are the three isotopes, why isn't the average atomic mass just carbon 13.000, because 12, 14, and 13, add those up, average them out, that's 13. Why is it 12.011? The reason for that is that not only do you take into account the different isotopes, the different mass numbers, but you also have to take into account the abundance. And because carbon 12 is much more abundant than carbon 13 or carbon 14, then because of that, the average comes out much closer to 12 than either of the other isotopes. Now, one thing about average atomic mass is that it can be rounded off to a whole number to substitute for the mass number, but this is only a last resort. Okay, this is only if you have no other way of figuring out the mass number. You don't have any proton information or neutron information, and you can't add those two together to get the mass number. You're not provided with the mass number. That is the only time that you use average atomic mass. They are not the same thing. Mass number represents a number of things, protons and neutrons. Average atomic mass is actually a mass. It's measured in units of mass. In fact, it's measured in the AMU, the atomic mass unit. And the atomic mass unit is based around carbon 12. One AMU is defined as being 1/12 the mass of a carbon 12 atom. So it's about 1.67 times 10 to the negative 24th grams, which is roughly the mass of a proton or neutron, which makes sense because protons or neutrons make up the vast majority of the mass of an atom. So 1/12 of a carbon 12, which has 12 protons and neutrons, should be about the mass of a proton or neutron. And like we said, atomic mass takes into account all of the different isotopes. So it's an example of a weighted average. And we're going to do some calculations here with average atomic mass. Boron has two isotopes, boron 10 and boron 11. So which one would be more abundant, given that the atomic mass of boron is 10.81 AMUs? Well, because 10 and 11 are right next to each other, and because 10.81 is a little bit closer to boron 11 than boron 10, we can make the assumption that the answer is boron 11, right? Because the 10.81 is closer to 11 than it is to 10. That must mean that boron 11 is more abundant. It has more weight in the average than what boron 10 does. Let's try one that's a little bit more involved here. Copper has two isotopes, copper 63 and copper 65. Copper 63 has a mass of 62.93 AMUs and accounts for 69.2% of copper. Copper 65 has a mass of 64.94 AMUs and accounts for the rest. What is the average atomic mass of copper? Well, the way to do a weighted average is that you multiply what you're trying to average by the number of, you basically multiply it by its weight. So in this case, we're doing weights by percentage. So what I'm going to do is I'm going to take 62.93 AMUs and multiply that by its percentage, which is 69.2%. And I'm going to add to that the other the other mass, which is 64.94 AMUs. and multiply that by its percent abundance, which is 30.8%. And then I'm going to divide the whole thing by the total number of parts to the abundance, which in this case, because it's a percentage, we're going to divide by 100%. All right. Now, math people, you're probably saying, can I just go ahead and multiply these by 0.692 and multiply this by 0.308 and not worry about dividing by 100? And the answer to that is yes, you can. But I wanted to show you this way to show you what happens to the percents. The percents, of course, are going to drop out, and we're going to be left with the AMUs in there. So I'm going to pause while I find a calculator, and then we'll come back and go over the answer. All right, and for a final answer, after putting all this into the calculator, we get 63.55 AMUs. And we have to ask ourselves, does this answer make sense? And if we look, 63.55 makes sense for a couple reasons. First of all, it is between 62.93 and 64.94. So it makes sense in that regard. It is between the two things we're averaging. And it also makes sense because it is much closer to the 62.93 than it is to the 64.94. And that makes sense because the 62.93 is much more abundant than what the 64.94 is. So we would expect it to be closer to the value that is more abundant. Now you can use the same process to solve for isotopes that, to solve for elements that might have 2, 3, 4 common isotopes. The method's pretty much the same. You're going to take the different masses, multiply them by their percent abundance, and then if you actually use percents, add the different values together, and then if you actually use the percents, divide by 100. If you don't, and you multiply by 0.692, by 0.308, or whatever it might be, you don't have to divide by anything. So that is how to calculate a average atomic mass. Now, how do they figure out what these actual percentages are? Well, they use something called a mass spectrometer. And basically what a mass spectrometer does is it takes a sample of an element and it breaks it down into, it basically atomizes the sample, and then it separates it into piles based upon how far those different isotopes are able to travel through a magnetic field. The heavier the isotope, the farther it's able to travel, and so what you really get are different little piles of isotopes. For example, if you're talking about carbon-12, you might shoot it into the spectrometer, and you get a little pile of carbon-12s here, little pile of carbon-13s a little further, little pile of carbon-14s a little further past that. And spectrometry has gotten so precise that we can actually identify where isotopes come from based on ratios. We might determine that a sample of lead came from a certain factory, or from a mine, or from Australia versus from Canada, based upon the different ratios of isotopes in that sample. So spectrometry has come quite a long way. And this information, again, is useful in IDing where samples might come from. Carbon dating is another example where something that's alive has a certain ratio of carbon-12 to carbon-13 to carbon-14. And once that thing dies, that ratio starts to break down more on the carbon-12 side. Carbon-13, carbon-14 will break down into carbon-12 over time. So the higher the percentage of carbon-12, the longer that once living thing has been dead. If there's not as much carbon-12 and there's higher percentages of carbon-13 and carbon-14, then you'll know that that thing has not been dead for very long. And that's how carbon dating can be used to sort of identify fossils that things that were once alive. It can be used to identify how long they've been dead, or how long they've been, where they're at. So good uses for isotopes and for identifying the types of isotopes there. And there's a picture of a spectrometer. And that is what the readout of a spectrometer looks like. And you can see, again, it's giving you relative abundance for different isotopes. So some pretty cool stuff, something you might do at the college level. We're going to go ahead and stop there, and we'll pick up with the mole next time. Thanks for watching, and we'll see you in class.